Welcome. I'm Andy Simon. I'm the product manager for our mechanical testing products here at TA Instruments. As you know, TA is a global leader in materials characterization with a wide range of instruments to characterize your materials properties. Today's webinar is going to focus on mechanical testing of polymers, but first I would like to introduce a few other TA instruments and techniques that can be useful for your polymer material characterization. First is our thermal gravimetric analyzer, or TGA. The TGA measures the weight or mass change of a material as a function of temperature, time, and atmosphere. The TGA can tell you about the thermal stability or the oxidative stability of your material, can estimate the lifetime of your product, and also look at the decomposition behavior of your material. Next is our differential scanning calorimeter, or DSC. The DSC measures the difference in heat flow rate between a sample and an inert reference to provide a very precise measurement of heat flow, typically as a function of time and temperature. The DSC can tell you about transition temperatures of your material, other exothermic or endothermic events, the heat of reaction, or specific heat capacity. The transition temperatures measured with the DSC are often the same ones that are measured with dynamic mechanical analysis, or DMA, which you will hear about more in the webinar. Many times people ask the difference between the two techniques in measuring these transitions. The DSC provides a great and very fast measurement of these transitions, but dynamic mechanical analysis provides a much more sensitive measurement of these transitions. Often the DMA can detect transitions that the DSC is not able to detect, and DMA provides a very valuable tool in detecting those transitions and also evaluating the effect on the mechanical properties of those transitions. And again, you will hear more about that during the webinar. And finally, we have our rheology instruments. Here we have our Discovery Hybrid Rheometer shown. So rheometer measures the viscosity and complex mechanical properties of liquids and semi-solids as a function of temperature and time. Rheology can tell you about the transient and steady state flow, dynamic properties such as complex viscosity, storage, and loss modulus, structural dynamics, and structural evolution, such as gel point and curing. You see terms such as storage and loss modulus here in rheology, and you will hear those terms again in the section about DMA. These are the same properties, but measured on liquids and semi-solids on the rheometer and on solids on the DMA, which provide a very different view of a material. So again, today's webinar is going to focus on mechanical testing of these polymers, but it is important to know the range of products that TA has to help in your material characterization. So with that, I would like to introduce Shoab, who will be giving the presentation today. Shoab has a background in mechanical engineering and completed his PhD at Clemson University, where he conducted research on multi-stable composite materials. After graduation, he joined TA Instruments as a field applications engineer. He has published several journal articles and conference papers on fatigue analysis and environmental response, and has developed mathematical, FEA, and machine learning models to predict failure characteristics and long-term material performance in service. His scientific interests are focused on mechanical testing and characterization of composites, medical devices and implants, and polymers. Without further ado, here's Shoab with the webinar.
Thank you, Andy, for the introduction. Hello, everyone. Thank you for joining this webinar. Today, I will present mechanical characterization of a polymer blend material, which combines polyphenylene ether, also known as PPE, and high impact polystyrene, also known as the HIPS material. Here, I will refer to the polymer blend as the PPE plus HIPS material. Let's start with the webinar. First, I will briefly introduce the mechanical testing instruments and software capabilities that TA offers that can be utilized to perform the characterization methods that I will share today. This shows the range of mechanical testing instruments from the smallest one starting from 200 Newton up to 15,000 Newton max load capacity. Almost all of these instruments can be equipped with torsion in addition to linear motion. This range allows us to find the appropriate instrument solution for many different material applications. Here you are looking at some of our tabletop instruments that are primarily the lower load range application instruments, starting from 200 Newton max load capacity up to 3000 Newton max load capacity. On the other hand, we also have our floor standing instruments, mainly for higher force applications, starting from 3000 Newton up to 15,000 Newton max load capacity. And these floor standing instruments, in their bottom housing, they can incorporate either an extended stroke motor or torsional motor to provide either additional deformation capacity or torsional motion. In addition to the load frames, we also have a line of instruments that are even more flexible, enabling many different configurations. Examples can include axial torsion systems, as you can see this one here, or a four-motor planar biaxial configuration like this one. You can see that these allow users to orient their motors and sensors in various ways to enable creative solutions for their applications. Each electroforce test instrument incorporates a high-performance linear motor. And this is what the motor looks like. There are 3 different motor sizes ranging from the size of a cube to half a meter cubed. And this design that is shown here is a patented electromagnetic and frictionless linear motor with bearing-free technology. This leads us to precise control of applied forces and displacements, ensuring billions of maintenance-free cycles. And it is supported by a 10-year-old motor warranty. Now I will talk about the software capabilities that TA offers with electroforce instruments. WinTest is the software that is included with each of our test systems to communicate with the load frame, specify both test and data acquisition parameters. It also includes ability to run many different waveforms or methods, integrated data acquisition, real-time control using broad range of sensors you bring into your system, limit monitoring for safer operation, as well as short and long duration tests, which can go up to 3 months without stopping. And for some specialized test methods, we offer additional applications that simplify the experience to one specific type of test, such as DMA test. And since we have joined TA, we also offer Trios as an additional data analysis software, which is very useful for comparing many data sets and also executing advanced data analysis such as TTS or time temperature superposition. All of our technologies that are wrapped into the instruments can be categorized into 3 groups: performance, reliability, and environment. We highlight the resolution and accuracy of our sensors, as well as the versatility of our instruments, which can perform monotonic, fatigue, creep, stress relaxation, and DMA test all in one instrument. Our instruments are highly reliable. In addition to that, a 10-year motor warranty, they can be performed in a very durable manner with minimal maintenance. These instruments have minimal effect on the environment in terms of releasing exhaust gas, can be operated in a clean and quiet manner, and they also do not need any hydraulic oils, which may need to be serviced and disposed of. For this investigation, we have actually studied a polymer blend material. While polymer material comes with specific advantages such as heat resistance or good electrical properties, it can also incorporate certain disadvantages such as low mechanical properties, flexibility, high processing temperature, low thermal stability, and high cost. To address these limitations, a polymer blend is prepared, which is a mixture of two or more polymers, to make a new material with enhanced properties. For example, compared to polymer A, polymer B here could be a polymer with high mechanical properties, high thermal stability, or even low cost. Thus, it can compensate for the disadvantages of polymer A. And thus, we have a new material or new polymer blend with enhanced properties. For this investigation, we studied the polymer blend of polyphenylene ether or PPE and high impact polystyrene or HIPS. Now, while the PPE material has high thermal stability, good electrical insulation properties, and also low moisture absorption, it also requires high processing temperature, as indicated by the glass transition temperature or TG of 215 degrees Celsius. It is also brittle at lower temperatures. On the other hand, the HIPS material has a lower glass transition temperature or TG of 90 degrees Celsius and has high impact resistance and ease of processing. When the PPE and HIPS material are combined together to prepare the PPE plus HIPS polymer blend, this new polymer blend has a glass transition temperature between 105 up to 170 degrees Celsius, depending on the ratio of the PPE and HIPS material in the polymer blend. This way, the manufacturer can acquire a polymer blend with enhanced processability and impact properties contributed from the HIPS section of the blend, while sustaining the advantages of the PPE material as well. For this study, we have investigated the PPE plus HIPS material by performing tensile testing and analyzing incline strength, performing fatigue testing, and we also have performed dynamic mechanical analysis or DMA tests and analyzed the results. The DMA test incorporates temperature ramp, creep test, time temperature superposition, or TTS analysis. I will start with the monotonic tensile test performed on this polymer blend. The tensile test was performed on specimens injection molded using a tool with single end gate. The testing was performed according to ASTM D638 at laboratory conditions. The results you are looking at here are demonstrating the behavior of a classical amorphous resin, which includes sequential changes within the molecular structure. We are looking at the stress strain plot for this specimen at 22 degrees Celsius, which demonstrate how the load-bearing capacity of the material evolves with respect to the applied deformation or strain. If we take a closer look at this stress strain curve, we can actually identify different regions depending on the material response to the applied strain. The first region that was identified is the linear elastic deformation region, where material deforms through linear and in a reversible manner. Then the material enters a nonlinear elastic deformation region. Here, the material is deforming nonlinearly, but still in a reversible manner, where if you remove the applied strain, the material will regain its previous condition. After nonlinear elastic deformation, with the application of additional strain, the material enters into the yielding region, which actually represents the transition from the plastic deformation to the elastic deformation to the plastic deformation. Tensile strength usually is measured at yield in this case. Then the material enters a plastic deformation region, as you can see here, where it is actually now deforming in an irreversible manner. And if you remove the strain, the material will still demonstrate some of the deformation due to that applied strain. After that, the region we can identify is the nicking region, where the material undergoes a localized reduction in cross-sectional area, which leads to a non-uniform deformation. Finally, with more strain applied, the material ultimately reaches a point where it can no longer withstand the applied stress, and it ruptures, experiences ultimate or global failure. The tensile test also provides indication of fatigue and creep response to characterize long-term performance of the material. For example, generally a lower tensile strength usually indicates to degraded fatigue performance. These tests are performed in this investigation as well. We have characterized our material performing creep and fatigue tests, and we'll share the results in the subsequent slides. Testing was also performed on specimens that are injection molded using a dual gate configuration, resulting in a neat line in the midsection of the tensile bar. A neat line is a location on a part where two flow fronts of molten plastic meet and fuse during the molding process. If the mating flow fronts are poorly fused, they result in relatively poor entanglement on a molecular level. This can be a relatively weak location on the molded part, which may lead to degraded performance or premature failure. We have actually utilized this dual gate sample you are seeing here to replicate a non-ideal condition that most parts have in some ways. It might be neat lines, voids, residual stresses, etc. These non-ideal conditions will almost never be on a data sheet, and they can actually have major implications in terms of material performance. The test results shown here for the dual-gated specimen identified by the orange curve, demonstrating that it had a modulus that was similar to the single-gated specimen. While the stress-strain curves of the two sample sets were nearly identical through the linear elastic region, here you can see, for most of the nonlinear elastic stages, a 16% reduction in tensile strength actually was observed for the dual-gate specimen. And the dual-gate specimen also experienced failure right around that neat line that we are actually considering as the defect in this case. Also importantly, the elongation at break was reduced from 32.5% for the single-gated specimen to 2.3% for the dual-gate specimens. These results are clearly highlighting that the primary effect of the neat line was the localized embrittlement of the material due to poor molecular entanglement. Usually fracture occurs within plastic materials as form of disentanglement, and the neat line here for the dual-gated specimen severely compromised the level of entanglement. This prompted the thought of characterizing their long-term performance by carrying out tests such as fatigue tests. Fatigue test is a characterization method where the specimen is cyclically loaded between two stress or strain levels, usually at a stress level which is below the ultimate strength of the material at a constant frequency. Here you are looking at an example of a material loaded under 4-point bending loading condition. When stress is applied on this specimen in a cyclic manner utilizing a sinusoidal waveform, and it is cyclically loaded until the material completely breaks and experiences global failure, the total number of cycles it survives is recorded. which introduces the concept of fatigue life. So fatigue life is actually the number of loading stress cycles that a specimen can withstand before failure. Usually, if the applied stress is equal to ultimate stress, the material will survive only one cycle. But if the applied stress is below the ultimate strength of the material, it will survive a certain n number of cycles, which is the fatigue life of the sample or this material. Usually in a fatigue study, repeating fatigue tests are performed at different stress levels, and the fatigue life n for each stress level is determined. Then a stress life or SN curve is generated, which can provide an estimation of the fatigue life of your material at specific stress level under certain test conditions. Here we are looking at the SN curve in correspondence with the stress strain curve from a monotonic test, where when you apply stress equal to ultimate strength, material is surviving one cycle. As we go lower and lower in terms of applied stress, the material is surviving higher and higher number of cycles. The shape of this curve can depend on the material and the test conditions, and this relationship can be linearized within a specific range, which is referred as Wöhler line. And for some materials under a certain or below a certain stress level, they will continue to survive and will not experience failure for an infinite number of cycles. This is a phenomenon that happens with some materials, such as composite materials, unidirectional carbon epoxy composites, but may not be observed in polymer materials. For this analysis, we have performed fatigue tests on a single gate and a dual gated specimen, both to generate the SN curve for both of these materials. The testing was performed on a tensile bar specimen using an electroforce 3300 instrument at a frequency of 5 Hz at 22 degrees Celsius. The stress ratio, or the ratio of the minimum stress to the maximum stress, was maintained at 0.1, and the test was performed in stress control. Here, compressed air was blown onto the samples as well to prevent material temperature change. And when we take a look at the test results, you see that the reduction in fatigue life in the dual gated specimen, identified by the orange dots here, compared to the fatigue life of the single gate specimen. We can observe that performing a fatigue test enables us to quantify that reduction in fatigue life as well as their long-term performance. We can see that at the same stress level of around 35 megapascal, the fatigue life of the dual-gated specimen is around a few hundred cycles, while the fatigue life of the single-gated specimen here is around a few thousand cycles, which is an order of magnitude difference in terms of fatigue life. So this is highlighting how you can quantify the material lifetime under certain loading conditions. Now, as illustrated here, the fatigue strength of the PPE plus HIPS material is lower than its tensile strength. Fatigue strength is the stress the material can withstand for a specific number of cycles before fatigue failure occurs. And fatigue failures occur due to the accumulation of damage to the polymer molecular structure over repeated cycles of stress, often which is well below the tensile strength of the material. In this plot, you can see the lower stress increases the life exponentially. For example, when the applied stress is lowered from 30 megapascal to 22 megapascal, there is an increase of fatigue life of approximately 10 times. This is an excellent example of the type of critical information that is typically not available from a resin supplier, but is essential to help make material and design decisions to avoid failure. Now I will shift gears and talk about DMA testing. A DMA test is a characterization method which is performed to quantify the elastic and viscous characteristics of a material under certain loading and environmental conditions. No material is a purely solid or purely viscous material. Rather, most materials are somewhere in between, being an ideal solid and ideal fluid. Take this rubber ball and tennis ball as example. If the rubber ball is released from a specific point, it bounces back to a point that is close to the initial release point. So the rubber ball was able to regain most of its energy or store most of its energy and lost a small amount of energy here as a form of heat dissipation. On the other hand, when we release the tennis ball from the same release point, it comes back to a lower height compared to the rubber ball. So the tennis ball is losing more energy as a form of heat dissipation. So in this case, the rubber ball is more elastic compared to the tennis ball, or you can say the tennis ball is more viscous compared to the rubber ball. So it is very important to quantify both the elastic and viscous characteristics of a material. And to do that, a DMA test is performed. The first parameter a DMA test determines is a phase angle. When a stress is applied and the corresponding strain is measured for a material or vice versa, the phase angle between the two signals is measured. For a purely elastic solid or elastic material, the phase angle between the two signals will be 0 degree. On the other hand, for a purely viscous material, the phase angle between the two signals will be 90 degree. Since most materials are between being an ideal solid and ideal fluid, that phase angle will be between 0 degree and 90 degree for most materials. Once this phase angle is determined, it is utilized to define the major viscoelastic parameters that I will introduce now. The first parameter I will talk about is the complex modulus, which is mainly the ratio of the stress amplitude and the strain amplitude applied or experienced by the material. Then to quantify the elasticity of the material, which is the ability of the material to store energy, the parameter called storage modulus is defined in terms of or with the cosine of the phase angle. There is another parameter that quantifies the viscous characteristics of the material, which is the ability of the materials to dissipate energy in the form of heat. And we call it the viscous or loss modulus, defined with the sine of the phase angle. Another very important parameter widely utilized is tan delta, which is mainly the ratio of loss modulus to a storage modulus. Tan delta actually quantifies the damping capacity of a material. The higher the tan delta, the more damping capacity the material will demonstrate. Here we are looking at the evolution of a storage modulus with respect to rising temperature. This is actually a general material behavior or material response for polymer material and may not represent the material behavior for many different materials. Here, heat is applied on the material in a temperature ramp test, which I will talk about in the subsequent slides. And the corresponding storage modulus response was measured. While going from lower to higher temperature, the material is actually transitioning from a glassy or more elastic state to a rubbery or more viscous state. Here at the lower temperature ranges, we can see that the storage modulus is staying consistent with the rising temperature. However, after a certain temperature level, the material starts to transition from the glassy elastic state to the viscous rubbery state. And during this transition, the storage modulus is dropping rapidly and the material is losing its stiffness. Then after this temperature point, the material completely transforms into the rubbery viscous state and the degradation rate of the storage modulus stabilizes. After that, after this temperature point, the material again starts to lose storage modulus in a rapid manner, and this is the point when the material enters the terminal region. And by the end of this terminal region, you can see the material loses almost all of its load-bearing capacity. Let's start with the temperature ramp test, which is a very common form of TMA test. In this test, a linear heating rate is applied on the material at a constant frequency and a constant amplitude. And the material response is determined or monitored in terms of storage modulus, loss modulus, and tan delta. This type of test is extensively implemented to determine parameters or material properties such as glass transition temperature. In this investigation, we have performed a temperature ramp test on the PPE plus HIPS material from negative 120 degrees Celsius up to 160 degrees Celsius and measured all three parameters: storage modulus, loss modulus, and tan delta. We will take a closer look at this plot by subdividing it into three sections in terms of the material response. When we take a look at the first section, which is our lower temperature range, we can see the storage modulus showed a stepped reduction with an onset at around negative 99 degrees Celsius, which is accompanied by a localized maximum in the loss modulus at around negative 87 degrees Celsius. And these responses correspond to the glass transition within the polybutadiene section or polybutadiene segment in the HIPS material. A glass transition temperature of negative 87 degrees Celsius was identified according to the convention of the maxima in loss modulus. And above that temperature, the material is more flexible and less brittle. In some cases, low temperature transitions like these are often associated with good impact properties. This type of secondary transition may indicate to improved impact property of the material at lower temperature levels due to the rise in the loss modulus or viscous properties. Now, at the midsection of the curve, between negative 65 degrees Celsius and 75 degrees Celsius, the material underwent a consistent reduction in storage modulus, which is accompanied by a stable rise in the loss modulus as well as tan delta as the temperature was rising. This represented a temperature-dependent gradual drop in stiffness, which is a classic behavior for an amorphous polymer below the primary glass transition temperature. This also highlights the rate and magnitude of reduction in storage modulus or across this temperature range, which will be very useful if this is the operating temperature range for the material during service. Now, as for the third section of the curves, here at around 120 degrees Celsius, the storage modulus showed the onset of a primary transition, which is accompanied by a localized maxima in loss modulus at around 146 degrees Celsius and tan delta at around 158 degrees Celsius. These transitions are associated with the glass transition of the PPE and the polystyrene miscible phase. A glass transition of 146 degrees Celsius was determined again according to the convention of maximum in the loss modulus. And above that temperature, the material had effectively lost all of its load-bearing capacity, as you can see here from the trend in the storage modulus. The presence of a single gross transition temperature indicated that the two polymers are homophasic. DMA illustrated as in this example provides key information regarding the structure and performance properties of your material. DMA is beneficial in material selection and product design, as well as part of the failure analysis, and can even be utilized for troubleshooting activities. We have also studied the creep response of this material according to or to assess the long-term performance by performing a creep TTS analysis. Before we talk about the creep TTS, let us start with a general overview of the creep test. A creep test is performed to evaluate the deformation experienced by the material at a constant load or stress level over a specific period of time. Importantly, creep occurs at stress levels which is usually below the yield stress or yield strength of the material, and at comparatively low stress, which is lower than what would cause an immediate plastic deformation. There is no opportunity for stress relief through yielding. Instead, at the molecular level, creep results in the movement of polymeric chains within the material, and over time, these chains can slowly slide past one another and disentangle, which can result in macroscopic deformation and even eventually lead to failure. Creep is actually one of the most common forms of plastic failure mechanisms. Now let's talk about the concept of time temperature superposition, or TTS. A TTS analysis works on the assumption that material response at longer duration can be simulated with higher temperature, and material response at shorter duration can be simulated with lower temperature tests. In the creep TTS test, a regular creep test is performed at different temperature levels starting from a low to high temperature. Then a reference temperature is selected. In this example, the creep test was performed from 30 degrees Celsius up to 145 degrees Celsius. And then 30 degrees Celsius was selected as the reference temperature. After that, the higher temperature curves above the reference temperature are shifted to the right according to a shift factor, and the lower temperature curves below the reference temperature are shifted to the left to generate a master curve like this, which represents the material behavior at this reference temperature, which is in this example 30 degrees Celsius. Here, the shift factor is determined utilizing empirical mathematical models such as WLF model, which is extensively studied in both academia and industry. And you can find a lot of available online resources to learn more about this method. Now, this curve represents an estimated creep response over a long duration under creep loading at a reference temperature of 30 degrees Celsius. And for this example, the data provides estimation across a time range of approximately 0.1 second up to 10 to the power 12 second, which is almost 300 centuries. So TTS is actually both a qualitative tool for material comparison, but also a quantitative tool that can be used to predict the material behavior. As we continue the characterization of the PPE plus HIPS material, HIPS testing was conducted with one of our TA equipments. And as I have talked about in the previous slide, that this involves performing a series of isothermal tests in short term, starting from low to high temperature, and then combining those material response curves together through time temperature superposition, or TTS, to create a creep master curve. In this case, the master curve was generated for modulus over time. And testing was performed on specimens injection molded with both procedures, single gate and dual gate configurations. And if you remember, the dual gate configuration actually presented a neat line in the middle of the tensile bar representing a defect. And this defect actually is also a representation of localized poor entanglement on the molecular level. The findings are consistent with the findings from the tensile testing. The creep test results are demonstrating that the initial modulus values were consistent between the single gate and dual gated specimens, as you can see during this initial period here. However, over time, the modulus declined significantly more rapidly for the dual gated specimens. This plot is an indication of deflection over time due to creep, and this information can be used to predict the magnitude of your material deformation from creep and understand when a material may creep and no longer perform its intended function. Some examples of material experiencing creep during service will be cloth hangers, bookshelves, ceiling surfaces, etc. Further, predictions or projections were made for effective creep lifetime for the PPE plus HIPS material under a stress of 25 megapascal, which is well below the yield point of the material. This plot is actually directly indicating the creep rupture or fracture of the material. When there was no lead line, which is represented by this blue curve here, the projected material life exceeds 22 years compared to 5 to 6 years with the material with knit line represented by the orange curve. This supported the previously conducted findings from the fatigue testing, which showed a dramatic reduction in fatigue lifetime as well, associated with this presence of a knit line. This is important for ensuring material won't crack over time from creep in things like press fades, snap fades, threaded fasteners, or even residual stresses from manufacturing. Now we will take a look at the creep data and make a comparison from a different perspective, which is in terms of total duration or total lifetime. Here, when we compare in terms of a 1-year lifetime, the material with knit line, which had no defect, can survive or withstand 40 megapascal of consistent stress. And that stress level is reduced to only 28 megapascal here with the material with knit line or with the defect. If we look at 5 years performance, the material with no knit line can survive 38 megapascal, which is reduced to 25 megapascal for the material with knit line. And this allowable stress level the material can withstand reduces from 37 megapascal to only 23 megapascal for the material with knit line when we are looking at a 10-year period. The results from this study provides us with some key takeaways. The first one I will talk about is that the information acquired from these tests can inform different stages of product development, starting from material selection, component design, manufacturing process, shipping requirements, as well as environmental and safety requirements. The service life of the material can be evaluated by implementing methods such as fatigue, creep, and TTS tests. I'd also highlight that a researcher or manufacturer can project the long-term performance utilizing these methods. For example, TTS allows a user to project the evolution of material response for very long duration, such as several to 100 years, which may not be possible to be evaluated by a manufacturer with the other available methods. And finally, the material properties indicated on a material data sheet are determined under ideal conditions and do not represent the actual properties of the molded parts. the datasheet is also limited in terms of providing information for specific environmental conditions. It is important to understand the actual characteristics of the form parts in order to avoid degraded performance and or premature failure. And the monotonic fatigue DMA tests demonstrated in this analysis each revealed a unique and critical information to understand the material response under the required service conditions. I would like to acknowledge that this study was performed in conjunction with Jeff Jansen from Medicine Group, who is an engineering manager at Medicine Group with more than 30 years of experience in polymer material characterization. We are very thankful to Jeff and Medicine Group for sharing their wealth of knowledge and experience with us. This brings us to the completion of this webinar. Thank you everyone again for joining here with me today, and I'll be happy to answer the questions from the audience now. Thank you.
All right, hello everybody. Thank you so much for attending. Now it's time for the questions. Please put them in the Q&A box, and I will go through and ask, kind of bring up the questions for Shoaib. And we also have Kareem on the line, who is a thermal analysis application scientist here at TA. So if you have any questions kind of in the DSC, TGA, or other thermal analysis techniques, please put them in the Q&A box as well. So the first question is how can DMA account for differences in material geometry, such as a tennis ball compared to a solid rubber ball, which will not have the same characteristics? So generally with DMA, the goal is to get the material geometry to something that can be easily entered into the instrument, into the software, and then convert the force and displacement measured, which kind of represents the bounds, into material characteristics such as modulus, which is geometry independent. That would be very difficult to do with something like a hollow tennis ball, especially when it's something of a composite structure. So if the goal is to analyze a material or maybe a composite of materials such as layers, but still have a consistent, say, rectangular geometry, those dimensions are entered into the software, and then that accounts for any geometry differences. If the goal is to analyze a part, we'll say, or a component, something with a complex geometry and structure, usually what we do is we don't attempt to get modulus, which is the material characteristic, but we get the stiffness, and we can get the storage. We can still get the storage and loss and tan delta, but as a sort of geometry dependent property of stiffness, which can then help use to predict the behavior of that component rather than a material. The second question, and Shoaib, this one's for you. On slide 27, the question is about the most important glass transition definition for the HIPS material. That with the peak temperature of tan delta would be considered a material glass transition, but that's not exactly what was said. So Shoaib, can you address that?
Yes, sure. Can you hear me clearly?
Yes.
Yeah, thank you for that question. The main reason for selecting the loss modulus as the primary parameter for defining our TG is because that is the parameter which was specified in the ASTM methodology. So this is the one parameter we picked for this investigation. And it is also possible that it matches better with other thermal characterization techniques such as TGA, DSC, and of course, loss modulus is a very good indicator when your material is reaching the peak of its viscous properties. But you can select a storage modulus, onset of storage modulus, or even a peak of tan delta to define your glass transition temperature. It can vary from application to application, but the most important thing is to, once you select one definition for your glass transition temperature, you stay consistent with that definition for your subsequent testings as well.
Okay, thank you. Next question here. Can tensile testing data be used to estimate the fatigue performance of a material?
It can provide a understanding of the general strength and also provide some indication for the starting point of your fatigue testing. But it cannot provide the estimation of the lifetime or actual quantification. For example, we saw that at certain stress level, the material is surviving a few thousand cycles. That type of quantification of your material lifetime is not possible with tensile testing. So tensile testing can give you some indication where to start your fatigue test, but it doesn't show the difference between using different blends. For example, even in this one, for two different processing methods, we saw two different types, two different degradation rate of your degradation trend of your fatigue life. So fatigue testing is, in those cases, is very important for quantifying long-term performance. In fact, we do have some data on polymer materials for different blends, which shows material performance in long-term for low cycle to high cycle fatigue tests, and which we are expecting to publish in next year. So to answer that question, in short term, the tensile test is limited in terms of providing projection for long-term performance, and you need to perform fatigue tests for that.
Yes, thank you, Shoaib. Definitely keep the questions coming in. We have a few more here. So next one is, how can DMA, tensile testing, and fatigue testing work together to provide kind of an efficient testing plan to characterize the material?
And as I have said, the tensile test will provide you a general estimation of the strength or quantification of the strength. However, you cannot perform tensile test for all different temperatures. Let's say you have 100 temperature steps, and that's where DMA comes in. You can perform a temperature ramp across a large temperature range and identify at which point your storage modulus or stiffness is having a significant change in terms of magnitude. And that will point you towards, okay, there's the temperature I need to perform my tensile my next tensile test set. And that will give you an indication too for the fatigue test as well. If you see a drop in your strength in that temperature level, after performing the tensile test, you can perform the fatigue test at the same temperature and estimate how much drop in fatigue life can happen at that temperature. So you perform a tensile test to know the strength, DMA test to know at which temperature level you can expect a change in properties, and then perform fatigue test at that temperature. That's how you can combine information from all three different tests to make material and design decisions.
Thank you. So the next one here, so we all know that plastic parts should generally be designed with the knit lines in lower stressed regions of the part. You don't want to put it where there is the highest stress. So are the fatigue properties of the, or the fatigue performance of that knit line really that critical?
That's a good question. Even if parts are designed with knit lines, and you're assuming that your knit line is located at lower stress regions, it will still not be absolutely zero stress. So there will always be some stress, and without quantifying materials performance at that stress level, you actually do not know if your low stress is low enough for a long-term reliable performance. And also this unfilled material showed a significant performance degradation for long-term properties, both in creep and fatigue test. If you are going with filled materials, then you can expect a much larger degradation in life and performance, because you will have either no or very limited fiber across that neat line. So with field materials, it is even more important to quantify your fatigue performance for those lower stress areas.
Okay, thank you. So the next one, how do we compare the knit line strength of injection molded components with the knit line strength data from this experiment? And also, how do we benchmark the polymeric material sensitivity based on knit line strength? Maybe start there. There's kind of a third part to the question, but maybe the first one, how do we compare the knit line strength of a component compared to the dog bone dual gate that we used in this experiment?
Okay, so both of the materials, both of the samples are actually of same material. The knit line here was actually introduced to replicate in non-ideal conditions, which can be a non-ideal condition from your manufacturing as a form of manufacturing artifact, a void or residual stress. So, so what we did was taking two materials formed by two different molding process, one with a single gate, one with a dual gate, and then perform tensile test on each of those same geometry dog bones. That's how we actually compared the knit line strength of injection molded components here for those dog bone sample. Here we were expecting the failure to happen right around that knit line because we know that because of that presence of knit line, there should be a poor entanglement in the molecular level. And the second part of the question is, how do we benchmark the polymeric metals of sequential injection process or in gate points in real life scenario on knit lines? Okay. Yeah. And you were saying something?
Yeah. So, you know, when it gets into real parts, complex parts, where the it's difficult to say simulate or replicate in a dog bone, a typical materials test fashion. Oftentimes, if it's a critical enough application, I guess maybe if I just take a step back. This dual gate knit line scenario that we created was intentionally sort of worst case. The materials flowed together in a, directly at each other in a flow front. It wasn't a meld line where they kind of came together gradually. So this was intentionally worst case. So you can use this data to bound the problem. That's one of the ways you can do it. The other way is sometimes you do need to actually extract a piece of the real component or test the complete component. Our ElectroForce mechanical test equipment is extremely versatile. There's many different ways to test samples. You can test dog bones as was shown, but we can also put whole parts in the instrument, sometimes connected to the T-slot table where you actually put the whole part on the table and then apply a load to it, or apply it in grips, or maybe a slice taken out of the material and then a load or a stress applied to it. And when you get into real parts, complicated molding behaviors, when you need to quantify that, that's generally our recommendation, is to find a way to get the real part in a test instrument somehow, because we can still apply very repeatable loads and displacements, but it's to the real part that experienced the real molding process. It's not always easy, but it is definitely the way to get the most accurate measurement of the performance of that component. So hopefully that answers that question. Just looking at the few in here still. So this one's on DMA. Can we apply TTS, or time temperature superposition, across temperature ranges for for which transitions are occurring, for example, below and above the glass transition temperature?
Yeah, the answer is yes, but you have to account for the change in stiffness that the sample is experiencing during the applied stress or strain as you go through the transition. But the good news is in all of our DMAs, we have a built-in feature, which is referred as force track, which is intelligently monitoring your change in stiffness with time, and it's modifying the mean stress or strain level that is being applied to the sample. So it ensures that if you're performing the test in tensile loading, under tensile loading condition, that material is always kept taut during the test. Or if you're performing a test under compressive loading condition, you are always maintaining contact with the upper fixture and the upper surface of your sample. So yes, you can do that, but you have to ensure that you are accounting for the change in stiffness in your material using this force track feature.
Okay, thank you. So we are already 5 minutes over time. Joab and I will remain on the call if anybody wants to ask any more questions. But otherwise, thank you very much for your attendance. And please reach out to TA if you have any additional questions or want to talk about your mechanical testing needs. Thank you.
Thank you.